All right, so I decided to make a model of the rotating bead on a rotating wire. So this is in Mathematica, and I just set k equal to 1, omega equal to 1, g equal to 9.8, and m equal to 1. And so the 3 steps that he was talking about in his video is to write down x, y, and z in terms of the cylindrical variable. So I just did that, right? And rho is a function of time, and phi is a function of time. But we also know that phi is a function of time, it's just omega t, and I just decided to make phi naught be 0. The kinetic energy you can just write this way. The potential energy you can write this way. And of course, Mathematica is going to do all of the conversions for you. In fact, if I ask Mathematica for what the kinetic energy is, it's going to be this ugly thing. But if I do simplify, then we're going to get, oh yeah, it doesn't quite look like what was in the video, but that's because I made so many of my constants be equal to 1. Similarly, the potential energy is just g mg k rho squared. So that's cool. And so then you get the Lagrangian, which is the kinetic energy minus the potential energy, and then we just have a differential equation. So here's the Euler-Lagrange equation, the derivative of the Lagrangian with respect to rho minus the derivative of the Lagrangian with respect to rho prime, and then another time derivative after that set equal to 0. Then I made rho at 0 equal to a really small number. I was curious if it was going to run away. And rho prime, I said, let's start it at rest and then go out to some maximum of 10. And I'm not even going to plot it. You can see it's oscillatory, right? So I can make a pretty picture of it, but it's clearly oscillatory. Actually, making a movie of it might be sort of cool. So let's see here. If I do manipulate graphics 3D, oh, it's kind of, well, I'll just do the point, I guess. Let's do point size of 0.05 or so, and let's make it blue, and let's do a point at x of t, y of t, and z of t, slash dot sol. That'll use our solution. As t goes from 0 to t max. Let's see what that does. Oh, why is it drawing it on a line? What happens if I... Oh, I see what's happening. Okay, so now let's go into graphics 3D and let's do plot range goes to 0.1 in all directions. Let's see if we can see it. Because remember, I started it at a really, really small number. Let's blow this up. There we go. So rerun this. So now here's this particle, and it should, yeah, it's going, it'd be nice if I could draw the paraboloid. I guess I could do that. But sure enough, it's absolutely stable. So what he said in his video was, I think if k gets steeper, let's see here. If I reduce k by a factor of 10, does it run away? No, but it's much less oscillatory. Let's reduce it by another factor of 10. Now it runs away. That's what's happening here. So yeah, so we can get things running away. Oh, man, that's so cool. But if I set it back to the original, get oscillatory, but now let's have this be way out. Oh no, it's always going to be oscillatory. Man, so interesting. Such interesting ways that you can model this. And so for me, the doing all of the steps that he talked about in his video, letting Mathematica do it right here, I'm sort of just stating how x and y and z are related to the cylindrical variables. And then I'm just doing everything with x's, y's, and z's. And internally, it's figuring everything out in terms of rho and phi. And then having Mathematica do this. So if I just copy this and paste it down on its own line somewhere, you can see what the Euler-Lagrange equation looks like. And then, of course, I could simplify it. It'll probably simplify down a little bit. Yeah, I mean, it's relatively simple, right? And so all it's doing is it's just, as time starts at 0, I'm going out to a maximum of 10 seconds here, and we're getting this really, really cool oscillatory thing, and that's what this video is showing here. So again, it's oscillating on the wire. How would I draw that? Paraboloid. That's tricky. I don't think, I mean, I know how to do it, but doesn't sound fun. So I guess I'm going to leave it alone. So I'll stop there. So this is just a little sort of way of, this is what the reaction video that I just did made me think of. So, all right, physics teachers are awesome. Have a great day.